Okay, so let's talk about a very important topic, one that should be appreciated by anybody who is interested in teaching or in learning, I should say, about any of the scientific disciplines, and that is the scientific method. So, the scientific method is basically a step-by-step process by which we investigate any particular phenomenon that exists in nature. And as I said before, it's a step-by-step process. So what we're going to do is go through each of the steps that is involved. But as stated here, when it comes to scientific knowledge, its nature is such that it is testable, reproducible, very important, explanatory, predictive, and tentative. So these are all the characteristics, let's say, of how we arrive at scientific knowledge of any particular part of nature. So the very first step involved in the scientific method is what is known as a hypothesis. We construct a hypothesis, which is basically a tentative explanation of what is observed, facts and observations, all right? Now, please note that this explanation, in addition to being tentative, it should be reasonable, all right? It should be a reasonable explanation. So we cannot just come up with any explanation. It has to make sense. In fact, it has to make sense in terms of being a very reasonable possible explanation for what is observed, all right? The next step in the scientific process is that we design and perform experiments. And this is particularly true in the natural sciences, chemistry, physics, biology, etc. Now, the experiments that are designed must be designed in such a way as to test the hypothesis. In other words, if the hypothesis is not true, then the test or the experiment will basically reveal that to be the case. All right? The term that we use in this context, we say that the hypothesis has to be falsifiable. In other words, the hypothesis must be such that when it is tested by experiments, then if it is not true, then the experiments will show that. If it is true, then the experimental data will be in harmony with the hypothesis. So as stated here, in experimentation, what we do is collect data, which almost always involve taking measurements. And we're going to spend some time talking about measurements later on in this chapter. Okay, so after we have done our experiments and we get our data, we look at our data to see whether or not the data falls in line with what the hypothesis would predict. Now, invariably, when we initially start off with this process, what you'll find is that the data will contradict the hypothesis, right? So what we need to do is to basically revise the hypothesis, or we ditch the hypothesis and come up with a new one, which will fit the data. And we continue that refinement process where we test the new hypothesis, get the data, see if the data lines up with the new hypothesis, change the hypothesis, or ditch it and come up with a new one, and we repeat that process over and over again. All right? When we get to a situation where there's harmony between the hypothesis and the data, then we designate that observation as a scientific law, which is basically and usually a mathematical description of what will happen. Here's what will happen. A theory is the explanation for the law. And basically, a theory is a well-established hypothesis established by the weight of the data as a result of repeated experimentation. All right? So basically, that's what a theory is. That's the difference between a theory and the hypothesis. A hypothesis is a tentative explanation of what is observed. A theory is an explanation, but it is backed by the weight of the data resulted from repeated experimentation to test the original hypothesis. So as an example of a theory, there's a theory known as the kinetic molecular theory. And this theory is used to explain several properties of gases. Now, one of the properties of gases is explained, or I should say, is stated by Boyle's law. Boyle's law says that the pressure times the volume of a gas is constant, provided that the temperature is constant, right? So that's what Boyle's law says. And Boyle's law is very predictive because basically if you know the pressure and you multiply it by the volume, you're going to get a constant value at the same temperature. It is the kinetic molecular theory that provides our best explanation for Boyle's law. So for example, if you reduce the volume of a container which contains a gas, then what that means is, according to the theory, the atoms, which are always in constant motion, will collide with the walls of the container more frequently, and therefore, as a result, create a greater force and exert a higher pressure, which is what is predicted by Boyle's law. Because based on Boyle's law, if you reduce the volume, the pressure would have to be increased in order for in order for PV is equal to a constant. So it's very important, and the reason why I'm going through all this here is that it's very important that you understand the difference between the law and a theory. The law is basically a statement of what we observe, for which there are no exceptions, while a theory is an explanation for the law, and that theory is backed by the weight of the evidence that was obtained as a result of doing repeated experiments. All right? So it's very important that you understand the difference between these different terms. Okay, so the next slide is basically going to show you a flowchart of what I just described. As I said before, in the case of the scientific approach or the scientific method, we start off with our observations, and then we test or we come up with a hypothesis for the observations, right? As we said before, it's a tentative proposal that explains observations, and then we test our hypothesis with a carefully designed experiment. The experiment is designed so as to test the hypothesis to see if the hypothesis can stand up to scrutiny. And as I said before, initially, and for most of the early part of this process, the hypothesis would fail, and therefore you'd have to, based on the experimental data, so you have to go back up here and you revise the hypothesis or come up with a new one. You test it further with more experimentation, and this process is repeated over and over again until you get some harmony between the data and the hypothesis. And when you achieve that harmony, you end up with what is known as the theory, which is the model which is based on the weight of the data that is obtained from repeated experimentation. All right? So that's basically what happens at this stage. Now, one thing I didn't mention, which I'm going to mention now, is that when you end up with a theory which is well established, that does not necessarily mean that's the end of the story, right? Because you can have a scientist, a researcher, tinkering in some lab somewhere, testing this established theory. And as a result of that experimentation, what you may find is that the scientist who is working on this would end up obtaining data which contradicts the theory, right? And what that means, therefore, is that you'd have to go back up here to come up with a new hypothesis to explain the data that is obtained at this stage right here, if it conflicts with the theory that we obtained earlier, all right? And you have to go through all this process again in order to get to your new theory, and even that will be established, or I should say tested by further experimentation. So not only do we test the hypothesis, right, by experimentation, but even the theory, even if it's well established, that also is subject to further testing, so that we can see whether or not the theory will stand up to further scrutiny. And if you look at the history of science, you'll notice that this is something that happens throughout the history of science, where you might have a theory that is well established by repeated experimentation, accepted by the scientific community, and maybe that theory stands for a couple of decades, even centuries, and then somebody somewhere comes up with some new data, some new information, which contradicts the theory. When that happens, then we have to basically discard the theory and come up with a new theory or a new hypothesis, which is subject to further experimentation until we get to a new theory, all right? Now, I want to highlight one example of this process. There was a theory that existed way back when. Let me open up this right here. Let me make sure that this is working. Let me scroll this down here. Okay, so, okay, ooh, my pen is not working. Okay, I don't know what's going on. Okay. I hate when this happens. Let me try something else. Let me try a blank PowerPoint slide. And let me do this. And let me select my pen function. Let's see if this would work. Okay, this works. Okay. Now, there was a theory known as a vitalistic theory. Let me write this down. Vitalistic theory. And basically what this theory says is that there are certain substances that exist in nature, that exist in the tissues of plants and animals, that can be only created in nature, and human beings cannot create these compounds in a lab. All right? So according to this theory, there's this thing in nature known as the vitalistic force. Vitalistic force that exists out there, that is responsible for the existence and the creation of natural compounds that exist in the tissues of plants and animals. You know, compounds like caffeine and oils and fats and all of that. So that was the belief back then, all right? I don't remember the exact years or dates when these ideas existed. So a guy by the name of Frederick Waller, let me write his name here. I think this is how his name is spelled. I think he was from Sweden, right? He was trying to isolate this compound. The name of this compound is ammonium cyanate, all right? Now, ammonium cyanate is an ionic compound, and we're going to learn about ionic compounds later on. In fact, you should have been exposed to ionic compounds in your introductory chemistry courses. Anyway, whenever people are synthesizing these compounds, and if it's in an aqueous solution, in order to isolate a typical ionic compound, what we do is heat it, and what that should do is remove the water, and you end up with your ionic compound in a solid state. And that's what Frederick Waller was doing. He did a series of experiments where he took several steps, and he ended up with this compound here in an aqueous solution. So he was trying to isolate this compound by heating it to drive the water off. Instead, what happened was a new compound was formed. A chemical reaction took place, and this compound was formed. All right? Now, this compound is known as urea. And you may or may not know this, but urea is a compound which is naturally found in the urine of mammals, right? Like human beings and cows and goats and pigs and all of that, right? And this represents the first instance recorded of a naturally occurring compound that was actually synthesized in the lab. As a result of this discovery, which by the way was by accident, right? Frederick Waller wasn't trying to make this compound, as I said before. He was trying to obtain this compound in a solid state, right? And he ended up by accident making this compound. As a result of that accident, that signaled the end of the vitalistic theory, right? And of course, we now know that there's no such thing as a vitalistic force that exists in nature, because we are now able to, based on Frederick Waller experiment, we're now able to synthesize this compound, which exists in nature, in the lab. And since then, of course, there have been literally millions of compounds that exist in nature that have been synthesized in the lab as well. And therefore, as a result, no respectable chemist has any belief in this vitalistic theory. So this is one example of a well-established theory that has been accepted by the scientific community, in this case, the chemistry community, and then somebody out of the blue, quite by accident, came up with some experimental results which resulted in the theory being obsolete as a result, all right? And what this shows you is that science, chemistry, physics, and all the other sciences is a very dynamic field. Nothing is cast in stone. There's no sacred cows. Everything is subject to testing and questioning. And as a result, there are new discoveries being made, changes being made to previously established theories, and so on and so forth, all right? Okay, so that's basically, let me discard this. Let me go back to the PowerPoint here. So that's basically all that I have to say concerning the scientific method. All right, so we're going to stop here. The next video will be dealing with scientific measurements. All right.